Welcome everyone to this webinar titled Geothermal Reservoirs, Deciphering the Rocks Through Petrophysics. The series is brought to you by the GEODE consortium, which is led by Project Interspace and the Society of Petroleum Engineers, and is funded by the U.S. Department of Energy's Geothermal Technologies Office. My name is Deanna Morrison. I'm your facilitator today. It is now my pleasure to welcome our moderator, Selene Pedroza. Selene is a senior sales manager and geothermal drilling subject matter expert at Baker Hughes Well Construction. She holds a bachelor's degree in geological engineering from the Middle East Technical University. During her assignment in Turkey as an application engineer, she played a role in adapting enhanced drilling technologies from the oil and gas industry for the drilling of over 100 geothermal wells. Currently, Selene collaborates closely with the new energy and well construction teams to develop scalable and economically viable solutions for geothermal projects. I'll turn it over to you now, Selene.
Thank you, Diana. Firstly, I would like to thank GEODE Consortium for their support to develop this web event. I'm now pleased to introduce our speaker, Tom Bradley. He is an associate fellow in the Gaffney Klein Energy Advisory Division of Baker Hughes, specializing in the open hole formation evaluation. After graduating in 1996 from the Royal School of Mines, Imperial College, London, with a degree in engineering geology, he started his career in 1997 with Western Atlas International. Since then, he has worked for Baker Hughes globally in a variety of technical and supervisory roles. Since 2005, he has been based in the Netherlands, and as part of his current role, he is advising multiple stakeholders in the development of geothermal energy in the Netherlands and Europe. I will turn it over you now. Thank you.
Thank you very much, Selene, and thank you very much, Diana. And thank you, everybody, for joining. It's my pleasure to, present my webinar, GEODE series webinar, Geothermal Reservoirs, Deciphering the Rocks Through Petrophysics. And as Selene mentioned, I'm Tom Bradley, an Associate Fellow with Gaffney Klein Energy Advisory with Baker Hughes. So, geothermal energy. And I like to start with these presentations because I'm sure many of you on the webinar are very familiar with geothermal. Some of you may be not so familiar with geothermal. So I'd like to start off by just a quick introduction. What is geothermal energy? And to do this, I've got a slide, one of the few slides I'm actually going to read. And this is actually courtesy of the US EIA agency, describing what geothermal energy is. So geothermal energy is heat within the earth. So the word geothermal comes from the Greek word geo, which of course means earth, and therm, which of course means heat. So geothermal energy is a renewable energy source because, of course, as we all know, heat is continuously produced inside the earth through like radioactive decay in the core and also higher up in like the crust and mantle. So what do we use it for? I mean, people have used geothermal energy for many, many years. I mean, in many ways, in fact, geothermal is actually older than the oil and gas industry. I can give examples. For example, in the United Kingdom, you may have heard of a city called Bath, the Roman baths in Bath from like 2,000 plus years ago. Many other places in the world, Turkey is also a good example where Selene hails from, where, again, sort of geothermal energy, hot springs, used for bathing. But of course, recently, it's come much more uses, for example, to heating buildings and generating electricity. So a little bit of an overview of what geothermal energy is, and also a little introduction, what we can use it for. Now, next, of course, in this webinar, we're going to sort of talk a bit about petrophysics. So now I'd like to give a little description of what are petrophysics and formation evaluation. And again, I'm sure many of you on the call are very, very familiar with petrophysics, formation evaluation. Many of you, I'm sure, have got experience of many years actually doing both of these. But for those who have not, a little description. So petrophysics, again, another Greek term, petra, which means rock, and physic, which means nature. It's a study of the physical and chemical rock properties of the earth and their interactions with fluids. Now, of course, many of us are from the oil and gas industry, and we've been using petrophysics for many, many years. In fact, in many ways, since like the 1920s, when the first sort of wireline logs are conducted. And we know its value because, as we know, sort of in the oil and gas world, sort of like detailed petrophysical knowledge, it really is a key input into many of the decisions we make throughout the life of a project, all the way from, say, the initial exploration and discovery, through like the development and production of a field, all the way through to the final abandonment. Because of this, as I'm sure many of us know, oil and gas companies, we do actually pretty much very extensive data acquisition, both sort of wireline and LDBD logging whilst drilling, throughout the life of a project to get the information that we need. And therefore, its value is well known. Now, talking about geothermal, as we all know, or maybe we don't, but sort of, I'm going to tell you, sort of geothermal, as I say, is an industry. It's been around a long time, like since the Greeks and the Romans. But in terms of large-scale geothermal, it's really only been sort of developing, let's say, the last few decades. And of course, what we've found is historically, at least over the last few years, sort of formation evaluation in geothermal was somewhat limited. A lot of this down to costs. And as a result, formation evaluation costs money, acquisition costs money. Therefore, geothermal sort of being so, let's say, not so, how shall I put this? Let's say commercially attractive as oil and gas. Quite often, they didn't have the money for extensive formation evaluation. So data acquisition was often limited. Really, sometimes just what was needed. It might be as basic, for example, as, say, just taking a gamma ray log to identify formation tops, or, say, a caliper log for sort of borehole conditions for, like, completion decisions and so on and so forth. Quite often, say we want to know details about subsurface, where can we get this from? Quite often, like historical offset well data. So some of the talks I've done, some of the papers I've published, I talk about this. And what we often find is that in many places, for example, geothermal areas, we're looking for hot water. And of course, hot water areas tend not to be oil and gas areas. So therefore, often offset data will be limited because areas with lots of hot water, not much oil and gas. And of course, your average oil company is not going to drill wildcat areas in an area that's only known for hot water. So what does this mean? Quite often we have very limited subsurface knowledge. And of course, if subsurface knowledge is limited, what does that sort of imply? Lots of uncertainty when sort of developing projects. However, what we've been finding over the last few years as, say, the geothermal industry matures is that the benefits of having detailed subsurface knowledge is beginning to be realized. So the question is, how can this detailed subsurface knowledge actually benefit geothermal projects? Which is what I'm going to talk about in this webinar. So to start off with, I'd like to sort of talk about what formation properties are important for geothermal. But before I talk about geothermal, it might surprise you, I'm going to talk about oil and gas. So the question, say I asked many of you people on the webinar, you're an oil and gas operator, what do you want to know? What's important? And really, quite often it can be boiled down to four things. Where are the hydrocarbons? How much is there? Are they going to produce? And what's it going to cost? So what controls this? Really, you can sort of boil it down again to a few key petrophysical properties or formation properties. Things like your reservoir structure, thickness and aerial extent, your porosity, your hydrocarbon saturation, your formation permeability, and the hydrocarbon recovery factor. Like these list of properties often control what is important to an oil and gas operator. This is something we know over many years, but now thinking about geothermal, what's important for geothermal? And even many of you maybe have not so much familiarity with geothermal. If I asked you what formation properties are important for geothermal, I'm sure you could straight away shout a list of a few things, even with no familiarity at all. For example, temperature and permeability, effective porosity, and the presence of fractures. And what I'd like to ask is, if you're a geothermal operator, what do you want in these properties? Do you want high or low? And again, even with limited knowledge of geothermal, you can probably say straight away, we want these to be high. And the question is, why? Why do we want high temperature? Why do we want high permeability? Why do we want high effective porosity? And why do we want sort of a good presence of fractures, in particular open fractures? And even with sort of limited knowledge, we could say this. Let's say temperature. Obviously, we want to produce heat. So the higher the temperature, the more heat energy you've got present. So you've got more heat there. How about permeability? How do we get this heat to the surface? It's by flowing water. And of course, if your formations are better permeability, you'll get more flow, so more heat produced. How about things like effective porosity? We can think about this, is where is the heat stored in the formation? Of course, it's in the water, in the formation fluids. It's also in the rock matrix itself. So we need to extract the heat from the rock matrix into our working fluid, commonly water, to bring to the surface. So if we have a high effective porosity, we're going to have more surface area to actually transfer the heat from the working fluid, well, let's say from the formation to your working fluid, and also not to mention as I'm sure we know, high porosities often go hand in hand with high permeabilities. They're connected, so high is good. Now, why fractures? Why do we want a lot of open fractures? Again, lots of open fractures also have many of the sort of benefits of the above properties. As we all know, open fractures tend to be permeable. So lots of fractures, good permeability, more flow. Also, fractures have a very large surface area to volume ratio. So sort of more surface area to transfer the heat from the formation to your working fluid. Again, the benefits of better flow, more heat produced, more energy produced. But the question is that it? Is there anything else we might want to know? Maybe things not so obvious. So what the industry's found over the last sort of few decades is these properties can also be very important. Things like lithology and geochemistry, your formation water properties, your formation and reservoir structure, also your formation geomechanical properties. So why are these important? Reasons such as this. Let's think about this. I mean, we're producing water from the formation. In fact, in many geothermal prospects, you're actually drilling two wells. You're drilling one well to inject water into the formation to maintain your pore pressure, and a second well to actually produce hot water from the formation. And what you'll find with injection, let's say, for example, you're injecting formation water, or let's say an injected water that's not chemically or biologically compatible with the formation. Could that potentially cause scaling and plugging? For example, in your formation, if you've got plugging, it's going to restrict your flow. Equally, things like another formation water property, as we all know, formation water is often saline. Hot salty water, what's that do when it comes to surface? Of course, the salt is going to come out of solution as it cools down, potentially cause scaling in your pipe work, which will reduce your pipe surface area, pipe cross-sectional area from high to low, reducing your flow. Of course, reduces your heat production. And not to mention, quite often, as we all know, wells are completed with steel casing. What does hot, salty water do to steel? It basically dissolves it. So therefore, you may have corrosion problems that you need to account for. Things like formation and reservoir structure. As we all know in the oil and gas industry, formation structure plays a very important part, putting your well in the optimal position in your trap to produce the most hydrocarbons. It's the same with geothermal. Of course, you want a good structure to ensure good flow, better location, better flow, more heat. And equally on the injection side, to maintain your pore pressure in a doublet-based system. You want to maintain your pore pressure. Is your injected water going where you think it is? Now, finally, your geomechanical properties and things like rock strength, particular fracture strength, subsidence and seismicity, wellbore stability. Because, of course, when we drill these wells, we want to draw often deviated wells to get the maximum reservoir exposure. But, of course, deviated wells have to remain stable. So, therefore, knowing your geomechanical properties is crucial for maintaining things like wellbore stability. Now, going back to sort of fracture strength, rock strength, as I mentioned, we are actually drawing down the pressure in the formation to produce our formation water. As we draw down pressure, could this potentially cause things like fracture reactivation, fault reactivation? Of course, reactivating faults will result in seismicity. And I'm sure some of you may be very, very familiar with the events that happened not too far from me. I'm based in Den Helder in the Netherlands, and the Groningen gas field, which has recently been closed down because over the last, let's say, decade, they've had extensive seismicity. And as a result, just to protect the residents, the property in Groningen, they've actually closed this because of seismicity concerns. Equally, we could potentially have the same thing with geothermal. So therefore, knowing your geomechanical properties is crucial for mitigating and minimizing seismicity and subsidence. So that's a few things that we find are important. But of course, as I mentioned, the geothermal industry is a developing and growing industry. Is there more we need to learn? What don't we know? What is there still to find out? And many of us on this call will be experienced oil and gas professionals, experienced in other industries. Can we apply our knowledge we've learned over all these years in oil and gas to help the geothermal industry develop and grow? So now, that's a little bit of an introduction to geothermal. What is petrophysics? What do we need to know? So now to go in a bit more detail about the actual petrophysics and what we might need to know and how to determine some of these properties. I'd like to start off by introducing a simple petrophysical model. I'm sure many of you have seen this before, sort of a very simple rock model, breaking the rock down into its individual components and quite often what we need to know for sort of petrophysical interpretation, and what we measure with the various log measurements that we conduct. So this is an example of a rock, and can break it down in sort of several components. We have our solid part, our non-clay matrix, and our dry clay. And we have our porosity part, which is commonly filled by multiple different fluids. For example, our clay-bound water, our irreducible water, our movable water, our liquid hydrocarbons, and our free gases. So now to consider these in different parts, I've already talked about the dry clay minerals, the dry clay. So our clay minerals, and we also heard the term wet clay. I'm sure many of you are very familiar with this. So what do we mean by wet clay? We mean our clay minerals in our formation, things like our illites, smectites, chlorites, montmorilites, so on and so forth, also including the water that's bound into the clay structure. We can then talk about a term I'm sure many of you have heard of called shale. I'll start with dry shale. So what do we mean by dry shale? We mean the dry clay fraction of the rock matrix, and also a certain amount of the non-clay matrix. Now, what do we mean by non-clay matrix? We often talk about limestone, sandstone, and dolomite. So quartz, calcite, and dolomite. We can further extend this to our wet shale. So what do we mean when we talk about wet shale? We mean our dry shale, so our dry clay, the non-clay matrix part of the shale, but also including our clay-bound water. Now, common discussion points about petrophysics is where does your shale stop and where does your matrix and your porosity start? Again, a sort of topic of discussion among petrophysicists that's often sort of discussed in much detail. So a subject for a later webinar. But now we can talk about the part of the formation that's often key to know for geothermal, which is our porosity. Because of course, our porosity is what we are going to flow, where we are going to produce our hot water from. So a term we often heard talked about or spoken about is our total porosity. Now, what do we mean by this? We basically mean all the fluids in the rock spaces, all the liquids, all the gas, including our clay-bound water, irreducible water, movable water, liquid hydrocarbons, and our free gases. However, this is not all the porosity that's going to move. For that, we talk about our effective porosity. Sometimes also you heard the term movable porosity. So this is the porosity that can potentially move, where we talk about our irreducible water, our movable water, our liquid hydrocarbons, and our free gases. Again, another point of discussion is where does our clay-bound water stop and our irreducible water start? Often controlled by sort of things like pore size in the rock. So a brief introduction to a petrophysical model. So now we can actually talk about how we can determine some of these properties that will be of interest to geothermal. So I'm going to start off by talking about maybe one of the key properties, and if you even know nothing about geothermal, you'll say, what do we want to know? We want to know temperature. As I mentioned already, in temperature, what do we want? Do you want low or high? And generally, we always want hotter. Why is that? Hotter is better, because of course we are hotter, more energy, so more energy to produce. And for those that are sort of working in the logging industry, the formation evaluation industry, we know that the majority of wireline and LWD temperature sort of logging strings, they always include a temperature measurement. But the question is, which temperature does this record? Is it the true static formation temperature, which as a geothermal operator is what we want to know? And of course, I'm sure many of you now are shouting at the screen, the answer is no, it doesn't. We'll start about LWD, because logging whilst drilling, where's that temperature measured? It's in the wellbore. And of course, what are we doing generally while we're drilling? We're circulating. And what does circulation do to the borehole and the formation? It cools it down. It can often be significant cooling. I mean, it's not unusual for like tens of degree difference between the mud column and the deeper sort of native formation temperature. So your measured temperature can be significantly lower than your true formation temperature. Now, how about wireline? Now, when do we record wireline data? It's often recorded very soon after the drilling. Of course, we've stopped circulating, so what's happening to the wellbore? It's basically slowly recovering to the native formation temperature. However, it's still going to be cooler. So how can we get a representative true formation temperature? Now, fortunately, with wireline strings, as I mentioned before, quite often we'll record several wireline logging passes in a borehole. And what happens when we're sort of recording several passes? The borehole's actually warming up. So by plotting sort of the time, difference in time and difference in temperature between the various logging runs, the various temperatures, we can actually infer a static borehole temperature, a static formation temperature. I mean, the chart presented here is one example of one methodology of doing this. Other methods are available. Now, there's another way of doing this. I mean, of course, let's say, for example, we've drilled the well, we've completed it, cased it, and now the well is static. For example, we can run things like production logs, and many production logs, case hole logs, also include a temperature measurement. Of course, this is going to be some time after the drilling is completed and the well has had time to stabilize. So the temperature measurement that you take with the production log may be much more representative of your true formation temperature. And a further thing I've not covered on this slide, but probably should have done, is of course, in many places in the world, the formation temperature gradient is well known. So if you know your true vertical depth, you know your local formation temperature, you can infer your formation temperature from that method. So that's a bit on temperature. As I mentioned, another key property to know is your formation porosity. Now, I like to start off, for those of you who may be not so familiar with petrophysics, is what is porosity? And a very sort of simple description I can give. Porosity, it's a space in the rock. So, of course, the space in the rock is where your fluids can be. In terms of oil and gas, it's your hydrocarbons, formation water. In terms of geothermal sort of formations, it's your sort of working formation fluid, your hot water. And I've got two examples here, like a sort of an X-ray, well, that's an electron microscope photo of a Rotliegend sandstone. Here's your grains. Here's your pore spaces. You can also see your pore throats connecting the pores, which of course is where the water is going to flow through. On the right is an example of an Illinois dollarstone. There's actually two sorts of porosity here. We have our vuggy porosity. We also have our fracture porosity, our fractures, source of porosity. Now, what you might note interesting here, we have very large vugs here. And this is, of course, very high porosity. But these vugs are, unlike your sandstone, are not connected. So you can have a very high porosity here, but a very low permeability. And conversely, where you have fractures, you can see this actual fracture here is very, very, let's say, not very wide aperture. So you're going to have a low porosity, but potentially a very high permeability. I'll talk about permeability in a bit more detail later in the presentation. Now, quite often what you find, let's say you have a clastic formation such as the sandstone, that's demonstrated here by this Rotliegend electron microscope photo. You have a high effective porosity. You're going to have large pores, large pore throats. So therefore, you've got more fluid to produce, potentially better permeability, so more energy. And saying that, high porosity is often, but not always, as I just described, related to high permeability. So the question is, how can we measure porosity with logs? And I'm sure many of you are shouting at the screen now. Methods such as conventional logs, density logs, neutron logs, acoustic logs, and also combinations of these logs, say cross plots, density neutron cross plots, I'm sure many of you are familiar with, density acoustic cross plots, and acoustic neutron cross plots. There's also other methods, things like your advanced logs, things like nuclear magnetic resonance logs, dielectric logs, which I'll touch on in a few slides' time. Now, how to sort of determine porosity? And I'll start off with something like, let's say, the standard methods we use, density, neutron, and acoustic porosity. Now, some well-known sort of equations, many of you might know these equations. If we know our matrix properties, if we know our fluid properties, we can then actually infer our porosity from these measurements. I've got the two equations here, our density porosity equation. Sorry, density porosity on that side, acoustic porosity on this side. I'll start with acoustic porosity is equal to your measured compressional slowness minus your matrix slowness divided by your fluid slowness minus your matrix slowness. On the right, the density porosity equation, very similar. Your matrix density minus your measured bulk density divided by your matrix density minus your fluid density will give you your porosity. And I've actually got an example of this on the right-hand side of the slide. I've got like a simulated log here for a sand shale formation with a nice thick sandstone, with the acoustic tool reading a certain slowness, your density log reading a certain density. And I've got two graphs here of basically acoustic slowness versus porosity and bulk density versus total porosity. Simply by projecting these values from the logs onto this graph, we can measure the porosity here. An acoustic slowness of 90 microseconds per foot being about 30% porosity, and a bulk density of 2.15 grams per cc being a porosity of about 30%. There's also neutron porosity, which works a slightly different way. This works by a tool that emits high energy neutrons into the formation, or actually thermal neutrons to the formation. This interacts with the formation matrix and formation fluids. And then by measuring the neutron counts that come back from the formation, we can infer the porosity. However, these are sort of well-established methods, but there are some considerations with these. A first one, for density neutron logs, as I'm sure many of us are familiar with, these rely on strong radioactive sources, with, of course, the associated health, safety, and environmental concerns. Quite often, many geothermal operators want to try and mitigate health and safety concerns by not using strong radioactive sources with all the considerations that come with them. A consideration with density porosity. This measures total porosity. As you might remember on the slide I showed earlier, this is not necessarily all connected and movable. I'll go back to the example of that dolomite core I showed on an earlier slide with the large rugs, very high porosity, but not connected, so not necessarily going to move. Now, looking at acoustic porosity, I mean, that can be a very good sourceless or radioactive source-less source of porosity. However, acoustic logs tend to be insensitive to secondary porosity. Now, what do I mean by secondary porosity? Secondary porosity definition is porosity that is generated post-deposition. Good examples being fractures and vugs. And say, for example, we're looking at, say, limestone prospects, fractured igneous prospects. They can be very, very high in secondary porosity. So acoustic porosity may be insensitive to this and give you a non-representative porosity. Now, neutron logs. A long-established log can measure porosity, but as many of them, sure, many of us know, can be influenced by many, many things unrelated to porosity. Things like borehole properties, formation fluid properties, neutron absorbers in the formation, so on and so forth. So may not read the true porosity. With all these measurements, you might notice these slides, these equations both have a matrix component and a fluid component. So therefore, to derive these porosities, we need to confidently know our fluid properties, say for example, our fluid density, our fluid slowness, or our matrix density, matrix slowness, so on and so forth. So say for example, we have complex formations, good examples being shaly sands, let's say a dolomitic limestone, even some of the more complex formations like igneous formations or metamorphic formations. Are we going to know our matrix density, our matrix slowness confidently? And let's say we have sort of like mixed salinity waters. Are we going to know our fluid density confidently? Are we going to know our fluid slowness confidently? As you can see, if we don't, we may have some uncertainty on our porosity computations. So how can we potentially, let's say, mitigate this and get a more confident porosity? I'm sure some of you may be familiar with nuclear magnetic resonance logging. I'm not going to go into the physics. I can talk about this for 2 weeks, and I have done. But put very simply, nuclear magnetic resonance logging tools, these use the same physics as a medical MRI scanner, which I'm sure some of you may have had in your life. And in terms of well logging, these essentially only respond to the hydrogen in the formation. So we have a clean formation. Where's that hydrogen? It's going to be in your pore fluids. So therefore, NMR logs only respond to the formation porosity, the fluid fraction only. And compared to sort of like traditional porosity measurements, they've got some benefits. It can also tell us the fluid let's say the porosity fraction in terms of small, medium, and large pores. And of course, if we know the distribution of small, medium, and large pores, we can then start to determine what's our clay-bound porosity fraction, indicated in this chart by the grey shading. What is our irreducible porosity fraction, indicated by the orange shading? What is our movable fraction? In this slide, indicated by the yellow shading. This is an example of a geothermal prospect I may talk about a bit more in the presentation that's sort of drilled and logged recently, this being very clean sandstones. And you can see in our sandstone intervals, indicated here by our density neutron, low gamma ray, we have lots of movable porosity, very clean formations, a very low shale volume, very low gamma rays, hence very low clay-bound porosity. So, of course, we know the porosity fraction. We can then start to sort of infer permeability from this, which I'll talk about in a few slides' time. Another benefit of NMR logs is these do not use radioactive sources. So, therefore, they are inherently safer than some of the traditional measurements such as density and neutron. Therefore, for an operator who, say, wants to, let's say, reduce their risk exposure, reduce their HS&E exposures, these can be very beneficial measurements. And this is the measurements getting a lot of interest in the industry, sort of porosity distribution with no radioactive sources. So some of the other advanced logs that could be of interest is dielectric tools. So dielectric tools have been started to be introduced to the industry, let's say over the last decade or so. And these tools tend to only respond to your water fill porosity. And because of the way these tools work by multi-frequency dielectric measurements, they are also sensitive to things like formation salinity. I spoke earlier about one of the properties of interest is formation water properties, in particular formation water salinity. So these can be actually used to derive some information on formation water salinity and also formation textural properties. For those of you familiar with the Archie equation, things like your Archie M and N properties can be derived in certain circumstances. So therefore, quite interesting for things like reservoir quality, formation water properties. Could this be a potentially interesting or useful information, useful measurement for the geothermal industry? Watch this space. So that's a little on porosity. So now I'll talk about permeability. As we all know, porosity is quite often related to permeability. As I mentioned earlier, high porosity, high permeability, and vice versa, but not always. And one thing you'll commonly hear in the geothermal industry, they'll say flow is everything. Now, why is this? Because you think about it, you're producing more hot water with a higher temperature, you're going to have more energy produced. As I mentioned before, what controls flow in a formation is permeability. Now, a definition, what do we mean by permeability? I'm sure many of you are screaming at the screen now, permeability, it's the ease of how fluids flow through a formation. And we measure it in darcies, or more commonly in formations, we're talking about millidarcies. So the question is, how can we measure it? Now, there's many methods. Going back to what I said earlier about permeability often being related to porosity, there are sort of simple, let's say, methods have been used many, many years, simple like porosity permeability relationships. I'm sure some of you might have heard of the TEMO relationship, with the assumption that as porosity increases, permeability also increases, so greater flow. And a little cartoon sketch here, sort of, let's say, for example, these might be core points where permeability and porosity is measured. You can do a regression and fit a best fit line through this to get an equation relating porosity to permeability. However, you might notice here, this isn't always the case. There's a few outliers. Good examples being, let's say, for example, we have a vuggy formation. As I mentioned earlier, you might have a very high porosity, but a very low permeability because the vugs are not connected. Now, vice versa, you might have a fractured formation. You have sort of like fractures, very high permeability because very good connectivity, but fractures, quite narrow aperture, so therefore low porosity. So it's not always the case. You'll find these can often work very well in, let's say, clastic formations, but you're going to say hard rock, fractured granites, fractured metamorphic formations, you're going to vuggy carbonates. These relationships can start to fall down. So are there other ways of doing it? Now, going back to NMR, I talked about NMR earlier. It can tell us our pore size distribution in terms of, I'll go back to actually this track here, this is what we call the T2 distribution. Now, the way to read this, if you have a lot of peaks to the left, it means you have lots of small pores. If you have a lot of peaks to the right, it means lots of large pores. A lot of peaks in the middle, it means medium-sized pores. And by partitioning this T2 spectrum, we can determine our clay-bound porosity, our irreducible porosity, and our movable porosity, which is, as I showed earlier, sort of signified by this track here with the shading. Now, for example, you might have heard of equations like the Coates equation, which is basically a way of relating this difference in porosity distribution to your permeability. Now, it doesn't take too much of a thought experiment to go from, let's say, for example, you have a formation with lots of movable porosity, lots of large pores, very few small pores. You can infer this is going to have a high permeability. And vice versa. You have a formation, for example, this shale here, with a very low porosity, low amounts of clay-bound water, and all the porosity is clay-bound water, small pores that won't move, none or very little movable and irreducible water, you're going to have a low permeability. Now, this is the basis behind the Coates equation. Permeability, K, is equal to your effective porosity divided by a coefficient C to the power M, multiplied by your movable porosity divided by irreducible porosity to a coefficient N. And this red curve in this track here actually represents the Coates permeability for this formation. Again, this is a geothermal prospect that was drilled recently. As I mentioned earlier, you have intervals with low porosity, only clay-bound water, no movable porosity. You have a low permeability. Conversely, you have an interval with high movable porosity, very low non-movable porosity, you have a high permeability. As mentioned, this works very well in clastic formations. But let's say, for example, you have fractured carbonates, vuggy formations. This relationship can start to be non-representative. It's also worth mentioning this is an empirical relationship. These coefficients M, N, and C need to be calibrated using local knowledge. For example, things like formation tester measurements, which I'll talk about later, or core tests. So unless these coefficients have been calibrated to sort of local references, this permeability is only an index. However, the actual magnitude differences are still relevant, and should these be calibrated, it can give a very sort of confident continuous permeability profile. Now, let's say, for example, you're in a vuggy formation or a fractured formation. NMR permeability can be somewhat non-representative. So then we can start to look at things like acoustic Stoney permeability. Now, for those of you not familiar with Stoney waves, this is a wave that travels along the borehole wall, and the velocity is controlled by the pressure pulse moving from the borehole to the formation and back again. And what you find is if you know your formation shear slowness, you know your formation density, you can predict the velocity of this Stoney wave. So then if we measure this Stoney wave with a logging tool, and you find your Stoney wave is slower than the predicted theoretical Stoney slowness from your shear and density, this is an indication of permeability. And the difference in your predicted versus your measured Stoney magnitude is related to the permeability magnitude. And what you'll find is this can be very useful in hard rock, so fractured and vuggy formations, because it's not influence from pore size relationships, it's the actual measurement of that pressure pulse from the borehole to the formation and back again. Good example here is we have, not so easy to see, but on this track here, we have plotted theoretical and measured Stoney wave. And if I blew this scale up, the actual magnitude difference is very, very small. We measure acoustics in microseconds per foot. It's only a few microseconds per foot, but a few microseconds per foot change can actually indicate an increase in permeability. Again, this is a recent geothermal prospect. The red curve is the Stoney permeability. The blue curve is the NMR permeability I described earlier. And in this case, being a clastic formation, well-connected pore throats, the coat's permeability works well. The Stoney permeability also works well and gives a good indication. What we often find by comparing Stoney permeability to NMR-derived permeability, it can tell us about the source of permeability. Is it fracture sort of driven permeability? Is it sort of pore throat driven permeability? So on and so forth. But again, something worth mentioning is, again, this is an empirical relationship. And it's important this permeability index curve needs to be calibrated to local knowledge. For example, core permeabilities, formation tester permeabilities, so on and so forth. So that's a little bit about two continuous measurements of permeability, NMR and Stoney waves. Another method of permeabilities I'm sure many of us are familiar with is permeability from formation testers. For those of you not so familiar with formation testers, the way these work is we have a pad, a snorkel, that's actually put down the borehole and pressed onto the borehole wall. And then with a pump inside the tool, we suck formation fluid from the formation into the tool and reduce the pressure. Then when we've sort of drawn down the pressure to a pressure below formation pressure, we can let this pressure recover and measure the rate, as indicated by this graph here, of pressure recovery back to formation pressure versus time. And as you can probably imagine, if you have a fast sort of recovery of formation pressure, this means the fluid is flowing quickly, therefore high permeability. If you have a slow recovery in formation pressure back to the native formation pressure, it means slow fluid flow, a low permeability. So this can actually tell us a direct measurement, technically, of formation mobility, because the actual measurement of these tools is also controlled by the viscosity of the fluid as it's flowing. Let's say, for example, you have a gas, which is a very low viscosity, it's going to flow quickly. If you have a heavy oil, that's have a heavy, very high viscosity, it's going to flow slowly. Water is somewhere in between. So if we know the fluid viscosity, these tools can also determine this with downhole formation, well, let's say downhole fluid analysis device I'll talk about later. By multiplying this viscosity by the mobility, we can get permeability. And then we can use these measurements to calibrate NMR and Stoney-derived permeabilities. It's worth mentioning these are not continuous measurements. These are point measurements. You have to sort of select the points where you're going to set the tool, measure the viscosity, if you're doing sort of fluid analysis, measure your pressure and pressure recovery. And by taking these pressure points throughout the borehole, you can give like measured viscosity, measured mobility points, which can be used to calibrate your log-derived permeabilities, such as NMR and stony permeability. So that's about permeability. So now to talk about some of the other properties I talked about that over the last few years, the industry has discovered are important to know. So I'll start off with lithology and geochemistry. So the question is, why are these important? Now, one key reason is you can imagine your lithology can be related to your total heat storage capacity of the formation. Some lithologies, some mineralogies have a higher specific heat capacity than other mineralogies. And you can imagine sort of working out your total heat capacity of the formation. These numbers are going to be important. Equally, lithology can be related to your geomechanical properties. Some lithologies are stronger than others. So, for example, when you're drawing down, let's say, producing your formation, thinking about things like subsidence and seismicity, these are important things to know. And not to mention formation fluids. As we are producing the formation fluids, as we're injecting fluids into the formation, the injected and produced fluids can react with the formation mineralogy, resulting in things like pore plugging, which will reduce your flow, things like dissolution or breakdown of the matrix, potentially, say, dissolving your cementing material can result in sanding. And those of you who sort of familiar with sanding in the oil and gas industry and producing through electrical submersible pumps, we know that sand and ESPs do not match well. You need ESPs to produce many of these geothermal wells. You have to replace your ESPs because of failure from sand erosion. That's an unforeseen cost, will affect your economics. So how can we determine lithology and geochemistry, or lithology and mineralogy? We've got methods such as conventional logs, gamma ray, density, neutron, photoelectric, acoustic, so on and so forth. This can tell us basic mineralogy, things like is your formation a sand, a shale, a limestone, a dolomite, igneous, so on and so forth. Things like spectral gamma ray tools, measuring potassium, thorium, and uranium, can give us, let's say, a little bit more detailed mineralogy, tells things like basic elemental composition, things like clay typing. The more advanced elemental spectroscopy tools measure the individual elements, and from this we can get more detailed mineralogy. And of course, methods like, say, rotary and percussion sidewall coring, where we actually go down with the tool into the borehole, take a small core sample from the side of the borehole wall, take this to surface, we can actually look at the piece of rock, tell us what it is. And also through casing, things like pulse neutron logs recorded through casing. These can tell us things like porosity, lithology, and saturation. So many methods. So now to talk about some of these methods in a bit more detail. And I'll start off with, let's say, I'm going to describe one of the most basic ways of doing it. Just looking at our conventional logs, our density, neutron, acoustic, and photoelectric logs, and just looking at the relationship of the measurements. I've got an example here of a simulated formation where I'm presenting bulk density, neutron porosity, gamma ray, and our photoelectric measurement from the density. And the formation is shale at the top, going into a limestone, then the sandstone, then dolomite, then another shale. Now, just looking at this, you can see some certain relationships, although it's worth mentioning the neutron tool here is recorded on what we call a limestone matrix. So it's designed, or let's say calibrated and characterized to read the true porosity in a water-filled limestone. Now, in the case of these formations, the limestone, sandstone, and dolomite are all 30%. So you can see on our 30% limestone, the density neutron logs are sitting on top of each other. In our 30% sandstone, we have our density a little to the left, our neutron to the right. Our dolomite, our neutron is to the left, and the density is to the right, the opposite of the sandstone. So by looking at this, we can actually just look at the sort of the relationship of the logs and see what we're looking at. A 30% limestone on top of each other. The same would apply for different porosities. The sandstone, density to the left, neutron to the right. Dolomite, neutron to the left, density to the right. And I'm sure some of you are very familiar with the technique of cross-plotting. If we project these points onto a plot where we have neutron on the x-axis, density on the y-axis, these points will plot in a certain place, actually related to theoretical lines where these different lithologies will plot. And if we want the porosity, to actually read the porosity, they can actually take the midpoint of these points, and that will give us a quick eyeballed indication of the formation effective porosity. So that's a basic way, but let's say we want more detailed mineralogy. This way we can look at measurements such as elemental spectroscopy. And there's both chemical source and pulse neutron source that tells us this. And the way these work, by basically emitting high energy neutrons into the formation and measuring the gamma rays that come back, the spectra of the gamma rays, we can start to derive the elemental composition of the formation in terms of potassium content, thorium content, silicon content, calcium content, magnesium, iron, aluminium, silicon, and carbon. As we know, these are common rock-forming minerals, both in matrix materials such as limestone, dolomite, and sandstone, and also our clay minerals like illites, chlorites, smectites, montmorillites, so on and so forth. And by looking at the relative proportion of these elements, we can then start to infer our mineralogy. A good example here, we have this section here where we have very little silicon, lots of calcium, a fair amount of dolomite. So it's not too much of a, let's say, a thought experiment to work out this is probably a dolomite. Let's say equally have an interval with, let's say, lots of silicon. We've got a fair amount of aluminium, some sulfur, magnesium, and iron. So potentially we might be looking at a shale here. Say, for example, we have an interval with lots of quartz, but very little magnesium and dolomite. We could potentially be looking at a sandstone. And this is also useful because then it's telling us our mineralogy. I mentioned earlier, this is useful for things like predicting pore plugging, formation responses, and equally can help us with our density logs to get a confident formation density. Going back to the density porosity equation, one of the things we confidently need to know is our formation matrix density. By sort of working out a detailed mineralogy, we can derive this. Hence, we can then derive a confident formation porosity, which is related often to permeability. So now to talk about fluids, how can we get fluid properties, in particular water properties? As I've talked about already, your formation fluids can influence your geothermal system. Things like interaction of injected water and formation water to the formation, resulting in plugging or potential cement breakdown. Dissolved salts coming out of solution as the geothermal brine cools down, bringing it to surface. Things like plugging of your pipework and also scaling and corrosion of your casing. It can also be useful to know if things like hydrocarbons and other gases are present because these will have to be dealt with. So how can we get formation fluid properties, particularly formation water properties? Many ways. I mean, going back to sort of our standard logs, as many of us know, things like resistivity logging, nuclear magnetic resonance logging, dielectric logging, formation pressure gradients, pulse neutron through casing can all tell us about our formation fluid properties. Also things like water properties, looking at like pressure gradients from formation testing tools, our dielectric measurements, formation fluid samples, and also using things like resistivity and Archie equation can tell us about our formation water properties, things like salinity and salinity concentration. But the question is here, we talked about lots of individual measurements, but really the key is actually integrating all these measurements to get the big picture. Because one key point to remember in all formation evaluation is no single measurement is going to give you all the answers. The big picture comes from integration. And of course, integrating all these different measurements will give you the most comprehensive interpretation. And I've got an example here. This is actually a geothermal well that's logged recently, where we logged many measurements: resistivity, density neutron, nuclear magnetic resonance, and some other measurements that are not presenting, things like sidewall coring and borehole imaging. And by presenting the logs together, we can get a very good overview of this formation in terms of where our clean intervals are, where our shale intervals are, what our formation fluids in these clean intervals are. For example, low resistivity, telling us it's saline water. Again, going back to the NMR measurements, we have lots of movable porosity, very little irreducible and clay-bound porosity, therefore telling us high permeability by the red curve. Looking at things like our porosity distribution for the NMR data, you can see here got lots of large pores, therefore very high quality reservoir. Even interesting things looking at our resistivity data by looking at the difference between shallow and deep measurements. We can see here we have an invasion profile, again telling us we have permeability. So really, don't look at one measurement on its own, get the big picture, look at all the information together. And by integrating all these logs, it gives the big picture and sort of the full comprehensive interpretation of your formation. But of course, I'd like to actually give an example of this. How can knowing detailed subsurface knowledge benefit a geothermal project? And this is a case study I published a few years ago. To give you the background, We have, not a million miles away from where I'm sitting, we have a client who drilled a fractured geothermal, well, basically a geothermal well in a fractured carbonate. This is sort of the actual log data. We had a 113-meter open hole interval. And what was assumed at the time of drilling was that the majority of the interval would flow. And in this well, the actual operator acquired some logs, not many logs, just a limited logging program, just nuclear magnetic resonance logs and borehole acoustic logs. The reasons these were run was for porosity determination. I've got the logs actually presented here. So the first track is our gamma ray. You can see the gamma ray here is reading low, suggesting a very clean formation. The next track is our nuclear magnetic resonance T2 distribution. As I mentioned earlier, for those not familiar with how to interpret these, you can look at the peaks. If you have a lot of peaks to the left, it means you have lots of small pores, lots of clay-bound porosity. You have a lot of peaks on the right, you have lots of large pores, potentially movable porosity. Lots of peaks in the middle, it means sort of middling-sized pores. These are sort of most likely to be irreducible porosity that will probably not flow. What I have plotted over here is similar to what happened in an earlier slide, this distribution of porosity, with sort of the yellow shading indicating, where's my mouse gone? There it is. Yellow shading indicating movable porosity, blue shading indicated irreducible porosity, will probably not move, and your browny sort of dashed shading indicating your clay-bound porosity in the shell will not move. And straight away you can see here, just looking at this porosity distribution, we've not got that much movable porosity. In fact, if we actually did some computations on the permeability here, we've seen porosity to 15%, and in some intervals, permeability is up to about 200 millidarcies. Now, what we can do on this, we can do a quick net to gross some arbitrary cutoffs. Let's say we're sort of counting as, let's say, potential geothermal reservoir movable porosity formations as a minimum movable of 5% porosity, a permeability of 2 millidarcies. By doing a quick net to gross on this, we're coming up with a productive interval of 36 meters. So you do the calculations, about 0.32%. So we've gone from 113 meters to 36 meters. We've lost 2/3 of our interval. So things aren't quite looking so good. But what happened next? This particular client, this operator, actually did some production logs. They did a well test. And while they were doing the well test, they ran some production logs. So spinners, pressure and temperature, to actually find where the flow is coming from. And this is presented in this log display here. So for those of you familiar with production logs, I presented the temperature on this track with differential temperature here, and your spinners over here. So the way to read this is if your spinners are reading the same value, this means no flow is coming into the wellbore. Where you have a sudden change in the spinners, here it's going from low to high, this means that significant flow is coming into the wellbore. You can also see this on the temperature log, which is this dashed curve here. You have a significant temperature change at the same depth. So what's this telling us? It's basically telling us all our flow is coming from 1 meter of the wellbore. So we've gone from what we thought was 113 meters to 36 meters to 1 meter. So now 1% of the wellbore is flowing. So the question is, why? What's causing this? And even with limited data, we can start to sort of do some interpretations and find out why this is happening. So what I've got plotted here in particular is the borehole acoustic data that was run for porosity determination as the original objective. Now, what to look at here is these tracks here. This track here in particular is an interesting one because the way a borehole acoustic tool works, little cartoon here, have the tool in the borehole, the transmitter, and some receivers. The transmitter fires, energy travels through the formation to be received by the receivers. And by looking at this received energy, we can start to derive some properties of the formation. Now, what's particularly interesting is this track here. We have the actual wave data recorded by the tool. You have here strong waveform arrivals, but at the depth where all the flow is coming in, suddenly all this energy vanishes. There's no energy being recorded. So why is that? Then we can look at some other things. This particular track here is what we call a borehole reflection image. For those of you familiar with seismic, it works on the same principles. We have the tool firing energy, but it's not only energy traveling up the formation near to the borehole, this energy gets emitted into the borehole itself, the formation itself. So let's say, for example, you hit a feature in the formation that has an acoustic impedance contrast. What's that energy going to do? It's going to reflect. And if the geometry is favorable, that energy will reflect back to the tool. And of course, if we can filter this wave field to remove these direct arrivals and leave the reflected arrivals, we can then start to apply, let's say, standard seismic techniques to attempt to image these reflecting features. And this is what this track here presents. What you have here is the boreholes in the middle of the track, and either side, we are looking 25 meters either side of the borehole. How I'd sort of like illustrate this is, when you're looking on a log display, 25 meters, it's not too much. But think about the room you're sitting in at the moment. And maybe this room might be 2, 3, 4 meters across. Imagine looking either side of the borehole 10 times that distance. So you're getting an idea of how far out from the borehole we can see. And what you might see straight away is your eye might be drawn to this feature here. You have a strong reflective feature. If you project it to where the borehole is, it just happens to intersect the borehole at exactly the depth where all this flow is coming in. So how can we interpret this? Is this potentially an open fracture or fault, bearing in mind this is a carbonate prospect, where all the flow is coming from? So even with limited data, just an NMR log and a borehole acoustic log, we've started to derive a lot of important information telling us why all the flow is only coming from one depth. So here's a question for you. Let's say we didn't know this. Let's say we have no data at all, no information at all. How could not knowing information sort of influence or the success of a project? I mean, the first one is poor performance than expected. I mean, let's go back to that previous example. Let's say we put the project on production. We're thinking the whole interval's flowing, but suddenly one day that fracture plugs up and it stops flowing. You can have poor performance than expected. And of course, you've got poor performance. What's that mean for your economic return? It means less hot water produced, less energy to sell. Therefore, it's going to be less attractive to your investors. Let's say equally, let's say you have limited geochemical knowledge. Let's say, for example, you're flowing water through that fracture, it's cooling down, the salts come out of solution, plugs that fracture up. You've got your sort of plugging, but let's also say, as has been found with many geothermal operators recently, some of the wells that were drilled 15 years ago and were completed with steel casing are now having to be abandoned and re-drilled because they didn't sort of realize the implications of no formation water properties, water salinity, and this casing has basically dissolved. The wells are no longer stable, so they have to be abandoned and re-drilled. Of course, that costs money. Now, let's say on the geomechanical side, we're drawing down this formation, your drawdown pressure is too high, so it results in sanding. You've got sand being produced. This sand goes through your pumps on the surface facilities. It's potentially going to wear them, cause your pumps to fail. They'll need to be replaced. Another unforeseen cost. Now, what else? Talking about faults, going back to the previous example, let's say we draw the pressure down too much and it causes this fault to slip and move. Reactivation of fault seismicity. I'm sure some of you on the call know there's been many examples of this. I can relate sort of the examples of Strasbourg and Geneva, where noticeable seismicity has occurred in these geothermal prospects and production has had to be reduced or even stopped while the operators come up with the plans for mitigation of seismicity. And the question is, what else? What don't we know? What can we find? What can subsurface data tell us about the benefits for geothermal projects? So now I'll leave some final thoughts. At the moment, what's been realized now, the last few years, the value of sort of petrophysical and formation knowledge to geothermal is becoming realized. And unfortunately still, as we all know, subsurface data acquisition costs money. And the geothermal, let's say the economics of geothermal being more challenging than oil and gas, is often seen as, let's say, an expense that people are trying to minimize. We can see that many well-established oil and gas principles, evaluation principles and methodologies are equally applicable to geothermal. And especially those of us who are in the oil and gas industry, it's a great opportunity to sort of help the geothermal industry by applying the knowledge we've learned over the years and the industry has learned over the years. And many measurements of these properties could be very beneficial. However, the benefits may only become apparent many years in the future after the wells have been drilled. And when we need to know this information, let's say it's not been acquired, let's say at the time of drilling, it may be very expensive and impractical or even impossible to get this data later in the life of a well when the rig has gone, the well has been completed, sort of subsurface jewelry is in place, so on and so forth. And of course, the end result, by knowing this information, we've got the potential to increase heat production and of course, economic benefits of cost savings through efficiency optimizations of prospects throughout the life of a prospect. On that, I will say thank you very much for coming along, and I'm happy to take any questions or any thoughts, ideas, or comments. So thank you very much.
Thank you, Tom. That was great. Thank you so much. And it's now time for Q&A. If you haven't already, please click Q&A button at the bottom of your screen to send a question. And also please use the QR code that Tom will show in a minute to complete a brief survey about today's presentation. So Tom, I would like to get the first question.
Okay.
I am curious how LWD, logging while drilling, will help when we acquire these data during the drilling. In other words, do you see we can one day do reservoir navigation for geothermal?
Yes, very good question, because sort of goes back to sort of the observation I made about sort of putting the well in the optimal place, because we all know, very similar to oil and gas, we want to produce an energy source. And I mentioned earlier, what do we need? Temperature and permeability. So let's say you steer your well into the most permeable zone. What's that going to imply? You're going to have better flow, so more hot water produced, so more energy. So reservoir navigation, definitely, especially let's say people are now looking at extended reach wells. Maybe, of course, what we're doing in navigation, reservoir navigation, oil and gas, we're generally trying to steer into the, let's say, the highest hydrocarbon saturation zone in a producing well. But this, we're looking for something different. Of course, high hydrocarbon saturation, highest resistivity. But here we're looking for water. So the opposite, we probably want to steer into the lowest resistivity, because that's going to have the highest porosity and the most water to produce. So reservoir navigation and geothermal prospects, definitely, and something that's getting a lot of interest actually in the industry.
Awesome. Thank you so much. Now, I have one more question from Robert Gales. He appreciates our presentation.
Oh, hey, Bob.
And he's curious, what are the temperature limitations on getting this information?
Aha, this old chestnut, because this is something I find a lot when you talk about geothermal, is the first thing people think of is Iceland, with sort of like steam coming out of the ground and sort of high temperature boiling water. But that's not all of it. I mean, a good example is here in Europe, where the big interest in geothermal is district heating. And if you think about district heating, it doesn't have to be that hot. I mean, most of the projects are about 85 degrees Celsius. So if you think about the technology, that is well within the sort of the let's say the specifications of standard logging tools. And also the pressures aren't too high, a couple of thousand meters deep. So well within, let's say, the specifications of what we log all the time in oil and gas. And again, going back to LWD, your question there, Celine, is usually sort of the temperature ratings of LWD tools are lower than wireline tools. But again, if you're only looking for district heating greenhouses, it's only 85 degrees Celsius, that's not a problem. But then we're talking about things like your Iceland things. And also, I know, Celine, the work you've sort of done in the past in Turkey, whereas these are quite warm, and you're looking at actual ratings above, say, for example, your standard LWD tools. I know what is often done in these environments is things like mud cooling, because, of course, when you're circulating, you're reducing the formation temperature. So that quite often brings like your standard technologies down to below sort of their rated sort of limits. So therefore, we can still get the data. And again, a lot of companies are working on high temperature tools and sort of specialist tools for evaluating these geothermal prospects, especially your sort of your hard rock high temperature for electricity generation.
100% agree, Tom. We can mostly run the usual rated tools in a high formation temperature. 100% agree.
Yeah,
we have one more.
I very like this going actually to planning the sort of the acquisition jobs and ensuring everything remains within spec.
Yes, we have one more question from Micah Alexander. Are there any core analysis tests you would recommend?
Permeability. Again, it's sort of flow is everything, and one of that's basically the key thing that the geothermal operators often want to know is permeability, because flow is everything. So, in terms of core tests, the big one is permeability. Again, also things like as I mentioned, porosity, because often that's related, and then you can build these pore-perm relationships for transforming porosity to permeability. And again, things like mineralogy, going to as I mentioned, sort of known compatibility with your formation fluids. And something I haven't touched on this presentation, but a big, very important sort of thing for the course is your geomechanical tests. Because mentioning things like cap rock stability, avoiding reactivation of faults, accidentally fracturing the formations, which in many places in the world, especially looking at geothermal, is something you don't want to do, is knowing what sort of pressures you can put on the formation when producing, but avoiding fracturing is very important. And equally, things like cap rock shell sort of integrity, so you don't accidentally fracture your seal when you're producing or drawing down, and then sort of potentially contaminate sort of possible water aquifers above and below the formation of interest.
Thanks. Robert has another one. He appreciates your data sets and says, geothermal covers a great range of temperature and depth. What would you say is most critical in EGS and AGS systems?
Enhanced geothermal systems. Good question. I mean, enhanced geosystems, we're generally looking at fracturing. So one thing I actually haven't touched on this presentation, I've focused more on the petrophysical measurements, but of course, in enhanced geothermal systems, we're looking for fractures. And therefore, how do we find fractures? It's things like borehole imaging logs. Unfortunately, with the limitations of time in this presentation, I didn't have time to talk about this, but yes, borehole image logging is something that's absolutely critical for these sort of enhanced geothermal systems. And equally, things like borehole acoustic logging. Again, going back to the, say, permeability, stony permeability can be very useful. And of course, the borehole reflection imaging example I showed earlier, that can be very useful, saying, okay, your borehole image is showing fractures. Are these extending deeper in the formation? Because of course, you need fracture connectivity to actually get your flow to produce your energy. And what else? Geomechanical properties too. I mean, quite often, you actually want to fracture these wells to create a reservoir to actually produce. So again, things like borehole acoustics, combined with density for your log-derived geomechanics, for actually working out how to frac your formation, for example.
And another one from George. I hope I'm not mispronouncing your name. How do the thermal conductivity and heat capacity of the reservoir rock affects the long-term production performance of a geothermal well? This is not taking account on oil and gas business.
Very, very true. Again, that's a very good observation, because I mean, where is the heat stored in the formation? It's in the rock matrix. And of course, that has a certain specific heat capacity. And you actually want to extract the heat from the rock into your working fluid to produce the surface. And this is actually a very sort of bigger area of study, especially in the academic community at the moment. I mean, a good example, I've been working a lot with TU Delft over the last few years, and this is something they are doing a lot of research on, because like basically how much heat is there, how fast can they produce the reservoirs to sort of actually get this heat out over an economic lifespan, to actually basically how much can they heat up, how much heat can they provide, and that is the value of the reservoir. So a lot of ongoing research, and again, knowing your formation properties, quite often, put very, very simply, denser rocks can store more heat, put very simply. So even though like your bulk density, your temperature, you can start to infer how much energy you've got there. And another interesting thing is, let's put it this way. Of course, we know in an oil and gas reservoir, when you extract the oil and gas, it's gone. However, with the geothermal reservoir, it's going to heat up again.
Yeah.
The question is, how long is that going to take?
Yeah.
Is it 2 years? Is it 20 years? Is it 200 years? Is it 2,000 years? Again, knowing these petrophysical subsurface properties can actually help you determine that.
Yeah, great way. We have one question from Gavin Liu. He thinks this interesting. He thanks you, and he says, as we know, there are EOR technologies for oil and gas. Would you think what kind of such technologies can be first leveraged to the EGS besides to the water flooding, mostly using now curiously?
Oh, good question. Good question. I can tell you one thing is what you might be thinking of here. There's actually a lot of talk at the moment of, can we use carbon dioxide as a working fluid? Again, could that help be useful? Because things about the heat capacity, like things like critical points, phase transformation, so on and so forth. Is that potential? I mean, again, a lot of the EOR technologies thinking about injection are actually sort of transferable to geothermal. Especially looking at, say, I go back to the doublet-based systems. This is my main area of familiarity, where you need to inject a fluid into the formation to maintain the pressure as your hot water is extracted. So again, sort of a good crossover between sort of the EOR type work that's been done in the oil industry to geothermal, where it can be equally beneficial.
Thank you, Tom. Another one from Michael Alexander. Are you interested in capillary pressure testing?
Good question. Yeah, I mean, going to capillary pressure, I mean, obviously, quite often in oil and gas, we look at capillary pressure like saturation height functions for saturations. But Capillary pressure, good question. I mean, obviously it can be related to permeability. Think about pore throat sizes. So I'll think about the one. I'd like to say yes. Maybe a good sort of subject for further research and investigation.
Nice. And we have one question from Juan Rafael Barcelon. What are your advice for someone in the field of petroleum engineering who wants to transition to geothermal?
Oh, good question. Oh, because this is how I got into this as well. More curiosity more than anything else, because it looked interesting. And sort of being things like attend your local sort of professional chapters. I mean, good example, I know SPE is pivoting, has a lot of interest now in geothermal and do a lot of presentations, a lot of workshops. So go to those and just get to meet the people, and also other societies. I won't mention them here, competition, and sort of start to attend these, and you'll find there's a lot of interest in basically the geothermal world of what we can offer as oil and gas professionals. I saw at the start, maybe 8-9 years ago, we're somewhat seen as the enemy. But as the industry is developing, there's sort of, let's say, the understanding of what we can offer and how all the sort of knowledge and skills we have are equally applicable to geothermal, and how it can benefit and help the industry develop and grow.
Absolutely. Actually, this is how I started. I started in geothermal and then migrate to oil and gas. So
right.
It's fantastic how much more we can implement from oil and gas to geothermal.
Yeah. So the more I see, so the more you look at it, the more the parallels are just obvious. It really is.
Absolutely. Absolutely. I have one question. So we talk about the fractures and how we can leverage our logging while drilling for trace fractures or any kind of measurement, let's say. What about for lithium production? Is there a method that
this comes up a lot.
Yes.
This comes up a lot, because I didn't touch on this, but what people have noticed, especially in things like hard rock areas, is these geothermal brines do contain significant amounts of lithium, actually in commercial quantities. And this is a big area of research at the moment of how can we extract the lithium from the produced geothermal water. And this is not something, I do not claim to be an expert in this at all. I mean, one question I do get asked is, are there any sort of log measurements that can identify lithium? And to the best of my knowledge, there are not. Because we were talking about concentrations here, very low concentrations, looking in the order of parts per million. And to the best of my knowledge, there's no log measurement that will detect this directly. I mean, one thing that we can do, of course, is downhole water sampling. You take water samples, take them back to the lab, analyze them, then it will tell you you've got lithium or not. But of course, these are just point samples, not continuous measurements. The question is, look at the elemental spectroscopy measurements and mineralogy logs. Are there any proxy elements or proxy minerals we can look at and identify that are associated with lithium? A good question. This is a subject, I'll say, watch this space, because it's got a lot of interest in the industry. And actually, I've heard in some geothermal prospects, the income from the lithium will be more than the income from the hot water. So watch this space.
Robert has some comments. He's agreeing that getting fluid samples are the best method, and saltancy is a good area to look at for lithium extraction with geothermal.
Oh yes, definitely.
Thank you, Robert, for your comments. Are there any more questions? We can take more.
I don't see any more questions.
So if anybody does have any questions, I mean, the contact details on screen. You can try and find me on LinkedIn. I am on there. I'm not very active, but feel free to contact me through that. And I'll say thank you very much for coming along, and I hope you found it interesting.
Yes, and I wanted to remind everyone again to please use the QR code to complete a brief survey. And thank you so much, Tom, for this presentation. Thank you, Celine, for moderating. And thank you, everyone, for your participation in today's event. I hope you all have a wonderful day.